Samsung pioneered the idea of in-storage compute. It was called ISC. Young-Suk Kee, who is my friend and close collaborator and mentor, he has published very, very good VLDB and other papers. I'll have a reference to that coming up shortly. For a memory-centric company, it's a very good idea to work on an FPGA-based implementations. How many of you know what is the relationship between a PLD and memory? You can memorize any function and pretend to be computing, especially combinational and certain kind of sequential circuits can behave that way. FPGAs are proof positive that you can make lookup tables and compute with them. For a memory-centric company, FPGA is a very, very good thing to have a starter on your roadmap to building integrated compute close to memory. Why are fast data and big data different? They're different because we manipulate fast data as memory in things like CPUs and GPUs. That is what is shown over here. So this green shows how we manipulate fast data using load store instructions and with a lot of optimization. Load store optimizations make 1000x difference. And I/O, there is no optimization. I/O libraries are optimized by hand by Bill Bridge at Oracle and such figures who are stalwarts in their own industries. A good idea would be to kind of remove that separation. It's not just that we want to bring big data and fast data close. It's that we want data that is big and fast. Then how will we do it? Well, we have to take gobs of bandwidth that actually are available at raw NAND and remove the distance between it and compute and memory like semantics. So be aware of things like Parquet and Arrow, because what they do is they describe self-describing data formats that live on disk drives. And then if you move compute close to SSDs, then you can expose, for example, Arrow format, and you can have the best of both worlds. Data structures that travel between I/O domain and compute, just like two computes talk to each other using protocol buffs. Okay? Arrow and protocol buffs are the kind of cousins. You do this kind of thing, then you can expand optimizer scope into I/O domain. Without optimizers, nothing works. We are not quite here yet. Okay? So I need to talk to optimizers who will talk to me. I am currently doing simple forms of compute that go live in an I/O device, not in a memory device today. Flash as I/O, not flash as memory. So what I have to do is I have to work with optimizers that live at database level, because C compilers and Java compilers don't know how to deal with me. Okay? But database optimizers have been doing this for 40 years. 8 years at Tandem, that's what I learned. All performance problems can be explained as rooflines. So today there is a tax on NAND flash. It's called an Intel CPU. Okay? You put one of these in front of about 4 SSDs and it is on its knees. At 8, a couple of Intel CPUs are exhausted. Okay? What if you have form factors like NF1 where you can put 36 or 24 SSDs in a single NF1 chassis? Now you have two choices. You can keep with the current architecture where you are putting things in front of the SSD to compute with, or you can make the SSDs compute and develop a good scale-out architecture with compute in every SSD. So I chose to do the second. Okay? Architecturally, I've made a shift, and I'll share with you some proof points of where we are at. So this slide on the right then explains the idea how that would work. So the basis for it would be internal bandwidth that exists inside an SSD. The difference between hard disk drives and semiconductor SSDs is that SSDs are made of semiconductor technology, and you can apply things like semiconductor integration. Actually, Samsung has been shipping logic in flash packages. We are the company that has about a 5-year lead on the rest of the industry in terms of actually shipping logic in every NAND package for the last several years. It's homework for you guys to figure out which product it is and which solid state circuit conference paper you should read. We could apply more integration to that technology. We didn't want to make a 10-year program which is new controllers, new memory type, new packaging, and make the software industry wait 10 years to figure out whether this is a good idea. I think this works this way. So on the right, it is shown that when we get past this idea, the internal bandwidth will change the slope in terms of performance I can deliver from a fixed number of devices in a chassis. The independent scaling without the front end will take me past the roofline. This is the theory of what I'm saying. This is what we actually built. Okay? I joined in December. We put out a prototype in June internally. In October on Samsung Tech Day, we actually put out this part showing integration with Spark, financial industry codes, and a homegrown MySQL storage engine called ExtraDB, running TPC-H, TPC-DS benchmarks, some pricing calculations for financial industry, and a whole bunch of other things that we are doing internally. These are proof of concept. You wouldn't want to run payments on it. It's reference implementation that we make available to our customers. But what we have done is taken industry's leading 3D NAND and taken highly integrated Samsung controllers, taken industry leading FPGAs, the biggest single die FPGA you can find in the industry, and put these things close to each other with a private data path. Why a private data path? Because on most microprocessors today, peer-to-peer I/O is not what these microprocessors root complexes are optimized for. So if you have accelerator outside and you have flash inside, and then the flash tries to talk to accelerator over P2P using the host root complex, you don't get very far. So by having an internal data path, we are able to create what we call unlimited concurrency. If you can localize computation between an accelerator, such as an FPGA and a GPU, and flash memory using a private data path, then as you add devices, you also add bandwidth to the system. We have some early proof points that I want to show you. Many of you know how stock market works. Most of us, we read the price of a stock at the end of a day in next day's newspaper or whatever your favorite application. And we think that's where the stock closed. You actually don't know how much volume happened at what price during the day. But these financial guys, they all know their own tricks. They don't work with stocks like we do. Every analyst has his own pricing formula for how they sum up volumes and prices to create volume weighted average pricing. And they have VWAPs and TWAPs and the Wikipedia pages on all these things. I was talking to a hedge fund guy who has half an exabyte of TCP dumps of stock market data. Today, what happens to this data? It goes into a very famous storage company's filers, and the data hits the disk drive platters and goes dead. You cannot mine it. It's worthless. These companies have workloads like historical portfolio evaluations and so on. They cannot run these things. We are trying to make sure they can run it. So that's why the first thing we implemented is how many millions of operations can you do with regular SSDs fronted by an x86 versus using a few smart SSDs in your system. We're starting to show scaling past some roof lines there. Second thing, like we ran TPC-H benchmarks. This is a geometric mean of performance on the queries of TPC-H benchmarks. Third thing we did is we have some open data from several decades of airline performance. We ported a Spark optimizer, take Catalyst queries that Spark generates, run them through this partner company's orchestrator and optimizer to get scans, filters onto our FPGAs. And we show that as you add devices in the system, that the first time we move from a non-accelerated SSD to the first smart SSD, we get 4x. When we add another SSD, we nearly double the performance, and then we double the devices again, we nearly double the performance again. We're starting to see early proof points of scaling in the number of devices. I repeat, we are not past the roof lines yet, okay? We are on course to getting there. For those of you who sort of are interested in the details, there are two ways that you can put an FPGA and SSD controller inside an SSD. You could SSD up front, you could put an FPGA up front, you could actually physically implement a PCI switch that would take up all the real estate on the SSD for just the switch, FPGA and controller. So since the FPGA can emulate a PCI switch, that's what we did in our first implementation. So this is FPGA in front, and you can see that all possible data paths are activated inside this. SSD behaves like a regular NVMe SSD. It's fully secure. The FPGA cannot cause data to move from the SSD into any place where normal SSD block and file stacks would not have moved. It's safe to deploy. The FPGA's security, deployment, programming works through the usual means. There's a kernel mode driver that allows things to be configured partially or fully. And then there is a user mode driver that allows applications to access accelerated kernels using SDXL. The PCI device has 3 physical functions, 2 FPGA related and then 1 SSD related, and they work pretty much with the standard stack with one difference. This device has 8 gigabytes of DRAM on it. This DRAM can be used in many ways. It can be working memory for your acceleration kernels. It can act as I/O buffers. If you don't want to stream through from the SSD to the FPGA, you can do buffered I/O between SSD and FPGA, or any other way you deem fit. The question is, how do you allocate memory inside this? So it's driver managed memory. You make the same kind of calls that you would normally make in FPGA stack, such as in OpenCL you would call CL create buffer to allocate host memory. Well, you call CL create buffer to create allocation inside this DRAM over here. Then you can present that as I/O targets or working memory. So it's a pretty simple device, works in very standard ways, but just has a fast internal data path, and that does all the magic. This shows that standard stacks works, and this shows we have plans for doing other than financial and database calculations. Lots of applications. Some Stanford students are helping us explore genomics. Others are working with very large customers in science and log analytics. This shows how we set up the TPCH benchmark. At the bottom, there's a reference to a 2-year-old VRDB paper that we wrote when we first conceived of the idea of in-storage compute. Instead of running it on a core, we are running it on an FPGA. It runs at the speed and parallelism of hardware, but is as programmable as software. When you run TPCH queries, lower is better here. We see substantial acceleration. You do the same thing with Spark. This actually plots out the speedups that we are achieving on TPC-DS queries. We took a scan-heavy subset. If you approach a data set and some data scientist has a new idea, this kind of situation is called ad hoc query. So in modern day, when data runs companies like Valero and Gap, and it's not just regular technology companies, every company runs on data. So their productivity depends on how much speed up we can deliver on these queries and how much data they can actually use in their business. So these speed ups are actually quite impressive. This setup that was used in measurements was a 4-node setup with 2 smart SSDs in each node. We can do 2x4, 4x2. The performance depends on how many smart SSDs we put in the system, not in how many Intels we put in the system. Very, very interesting result. But the speedups are good. So what I did is I took one of these queries, and I'm just showing you a profile of how things are. I want you to notice the scales. The scales are substantially different between running with regular SSDs and smart SSDs. Everything just shrinks. There is headroom in there. Our scan-heavy queries are I/O bound queries. That is why we are able to shrink the time so much, because now we have moved compute to the I/O. The Catalyst plan included 2 large segments. That's what is shown in the blue profiles over here. That profile over there is from the accelerated run. I have not shown the profile from unaccelerated run. You can imagine that from the timeline charts you are seeing. Let me not go into this slide. I have presented this before. Let me leave you with this slide. What is the big idea and where are things going? We are kind of at this crossover of optimization, meaning building new technology and a new idea. We have compute acceleration and network acceleration. We do not have storage acceleration. Software people don't understand how to use it. And we don't know how quite to build it perfectly yet to be meaningful. And optimizers don't know how to optimize for it. Nothing is ready for us. So we are to the left of that crossover point during last year that we've been working on it, and during most of the next year. The reason we built a quick prototype is to kind of achieve this crossover. We are now starting to put these devices in the hands of interns, university partners, specifically our large customers. So we have built workloads tools. We have done integrations and APIs with stacks. I showed you early proof points of optimizations. We will start to do more integration, more packaging, more Samsung magic to take this to a higher level of performance, even as we de-risk it by enabling software technology to use familiar technologies. Okay? And we hope that we'll be delivering something really, really new and very innovative and industry leading. Again, thank you very much.